Now to the business. Today, the whole idea is to compute the mean and use it, the sample mean, and use it to estimate the population mean. And the big question we should ask ourselves when we do that based on 10 or based on 15 or 100 observations, I compute a sample mean, I should ask myself, how close to the true mu am I? What is the error I make when I claim my mean should be an estimate of the population mu? Am I correct or do I make a mistake? I know that I'm going to make an error. I will never hit it exactly. The question is, can I quantify the error that I might make? And the answer is, of course, yes. How do we do it? We do it by probability theory. But let's try it first. Let's try to simulate the challenge that we are having here with a little r thing to make you hopefully understand why we're doing what we're doing. I'm trying to decide that I know the truth. So this is a toy example where I'm playing around with what could hit us, right? What if the mu really is 178? What if the sigma is really 12? So that's a scenario-based thinking. What if I take a sample of 9? I can do that from the computer. I can do 10 randomly sampled persons. So I can simulate a random sample here. And now would be the time to actually go do it. I could do it again. That's the fantastic thing about. You see this? I can play around with taking samples of 10. This is a pretty neat feature of the computer, because now I can play around with how the reality could hit me.
But isn't it the same numbers?
Smarters. Thank you for that. Whoa. Thank you. I'm male. I can talk and then I cannot look what happens. But thank you. Of course, I should re-simulate each time to have something new happening. Thank you. And I was a bit worried what you were laughing at, so this was good that we found that. Let's try to compute the mean and the variance. I could also, again, I should remember to actually do the simulation. I can compute mean and variance, and I can do the plot. Here is different versions. Look at the mean and the variance, 176, 143. It's like the square root of 12. That the square of 12 is 144, so that would be the expected variance. But look at how different they come from time to time. This is very, very important moment in this class and in your life, what we're doing now. Can you feel it? Can you feel it sink in? Do you get the challenge? You only, when real life hits you and you're going to make a decision in your company, you only see one sample and you're going to make a decision for the future based on one sample. And look at the risk that you're having. You're the responsible engineer. It's your decision. If you make the wrong call, you're out. And look at how different it could be tomorrow. If I did it again tomorrow, this experiment, I get a different number. 185, 182, 173, 181. How the heck can I deal with this? Is it completely random to be an engineer in wherever? No, because first of all, I could realize that I know that I'm not going to get the same answer tomorrow. So I can make sure that my manager understands that. You can try. If your manager is a good engineer, he would understand. And he might very well be. We could actually extend this a little bit and actually do already here many such samples using the computer, right? Now I do 110 samples and I compute the mean of all of them. That's the interesting thing, right? What is the behavior of repeated means? Here's a distribution of repeated means. Repeated means are centered around the mean. That's one point. Repeated means are centered around the mean. And I get an idea of the variability of the mean, right? That's the meta thinking here. We're doing it very detailed now. That the mean itself is a random concept. And if I know the distribution of that one, if I can control, or at least I know how much it can vary, then I'm on top of the situation. Then I'm an engineer and I'm intelligent, so I can quantify this uncertainty and this variability. And in what I claim and in the decisions I make and the communications I do and the contracts I make that are due to those decisions, I can control it to make sure that I'm not going to be kicked out in case it comes out slightly different next time, because, well, we all know it could come out slightly different next time. So we need to be on top of that sampling uncertainty, the sampling variability, or even the sampling distribution of the mean. These are the words that we're going to use here. This is what we need theory for. That's why we need a theory that controls this behavior. I mean, and we cannot fix it to be deterministic, because it is a random behavior. But we can get on top of this random behavior by knowing how it behaves. So this is the core theory coming here as theorem 3.2, telling us what happens if I sample something, assuming it's a normal distribution for now. That's the assumption in the beginning. It's a very classical assumption in classical stats. If I assume that the phenomenon that the height distribution is a normal distribution such that the repeated heights, the 10 repeated height that I have, if I compute the mean of those and consider that as a random variable, that's why it's a capital X here, I know the theory here tells me what is the behavior of such a mean. And that's what I need. The behavior of the mean is that on average, that's what I said, repeated means will on average be the true mean. Obviously, somehow we wouldn't expect otherwise. And also, and that's the nice thing, repeated means comes with a distribution, which is the sort of population sigma, the 144, if it's the height, right, 12 squared, divided by the sample size. This is the big N that even makes a business here, right? Because we can increase precision by increasing N, right? Higher N, better precision. We would all have that feeling, gut feeling, that the more money we throw after a study, the higher the N would be, the better it is, of course. And this is the formula telling us the precision we have will increase with N. And actually, we could prove those statements based on rules that Peter taught you last week. And we are not going to do it using a lot of time here, but it is one of the few sort of proofs that we do in this course. The expected value of an average, of a random average, is, due to the rules, just the similar average of the expected values. That's one of the rules you were taught in theorem 256. And since each of them has this mean, when I add up those, it turns out here's the theoretical statement expressing that repeated means has the population mean as its mean, expected value. The more interesting thing here, the variance of an average. The variance of an average. How much would a mean, an average, change from time to time, from sample to sample? I'm trying to put that into formula here. What we saw in the picture, that it goes from right to left, it changes all the time. Here is the formula that tells me how much could it change from time to time. The theory comes here. How could I find the variance of an average? Well, they are assumed independent. It's not set here, but they are. So, a variance of, maybe I should even put it like this, the variance of this one, that's what I'm trying to find now. Trying to write slowly, then it works. Like this. The first rule is that the n goes outside, that's a constant, and it will be squared, that's the rule. Then variance of a sum, that's the sum of variances, that's another rule. So I get the sum of variances. All of the variances are the same, sigma. That's the population variability, the 144 if it was the height example. When I add up 10 of such variances, I get 10 times this individual variance, and all together, one of the n cancels out, and we have one n left. And this is the standard error of the mean, the sampling variability of a mean. Maybe the most important formula. Until next week, where I come with another most important formula for you. But for now, this is the most important formula of the course. And in a way, it's a very, very generic, really, formula. Let me elaborate a bit more how that can make us happy in the challenge we're having. Our challenge is, what big an error do I make when I just compute an average of some numbers and I claim, because that's the purpose of it, I'm going to claim this average is a surrogate for the truth. Because what could I do otherwise? I'm an engineer. I need some numbers to move on here. So I use the observed sample average instead of the truth, which I don't have. And I have to, if I'm a good engineer, I should think about what is the potential error I'm making. And it's basically the same information again. The standard deviation is just the square root of my formula from before, right? So there's sigma over root n. Sigma over root n. And to be even more explicit, that means that the standard deviation of the difference between my guess and the truth is the same thing, because when you subtract a fixed number from a random thing, it doesn't affect the variance. Another one of those rules from last time. Why do I look at this? Let me see. I look at this because this one, you could also call this is the random error I'm making, right? Please, if it's not clear to you, for some it's probably clear right away, for others maybe you have to get used to this. The difference between the computed average and the truth, that's the error I make. That's the one I should be concerned about and learn to deal with. I already learned a lot because I know how much such an error could change from time to time. That's good information to have. When I'm going to claim something, it's good to know the error of what I'm claiming, right? As I said, then we can put it into contract and I can protect myself. And also in the decisions I make, I can protect myself against this error. Here comes the same result in a different version. This is a similar version, but it's a version where we actually divide by this standard deviation of the mean, the one that I just found. Remember, you did some normal distribution exercises last time, and you could standardize a normal by subtracting the mean and dividing by the standard deviation, then you get the standard normal. And hey, you actually need to remember something what you learned the weeks before when you show up for 1 week, right? So next week, I'll assume that you have at least a little recollection of what we did today, right? This is a standardized error. The standardized error we are making when we make a decision in the company follows a standard normal distribution. Great. I know the probabilities from the standard normal, so now I'm in business. Now I can quantify with which probability I do various size of errors, right? That's pretty good. That's pretty good. But, we have a problem so far. It's a nice theory, but it's useless as it comes so far. Why is it useless? Because sigma is in everything here. Sigma is the true standard deviation in the population. I would only know sigma if I sampled 1 million people, for sure. And the theory here is relying on sigma being the true sigma. Bugger. Bugger, bugger, bugger. What do we do? Whoa, we're an engineer. I just learned how to compute a sample standard deviation that I called S. What's the big deal? Why don't I just throw in the S instead of this theory sigma? I know a value, I know an estimate of sigma, so I throw that in, and yes, of course, that's the answer. It's common sense, that's what we do. But then if you go to your probability class, the probability teacher will tell you, then what I just told you, those two theorems, they don't hold anymore, they break down. The normal distribution is no longer the right distribution to use there. Well, then we use the T. And here, let me introduce, first time, student's T, made by a statistician at the Guinness Brewery, called himself, used an alias. Student, he thought, was a good name to use as an alias. So here is a student's T distribution defined to you at least indirectly. We don't see any density formulas here, but we see something else. We see a theorem, which is almost the same theorem that I just showed you, where we have a more realistic version that we can use now. This version tells us that standardized errors we make, standardizing by something we actually can find, the S, follows not a normal distribution, but a T distribution. Here's the difference. The T distribution comes in different disguises or in different versions because it depends on the N. We use this terminology that if I have N observations, we say the name is the T distribution with N minus 1 degrees of freedom. Just a name specifying that there are many different T's, one for each N, basically. And here's a version of, with the black, I showed you the standard normal distribution here, and as in the red, I showed you a T distribution with 9 degrees of freedom. The T distribution is, for practical purposes, very similar to the standard normal. That's sort of how we should think about the T distribution. It's a standardized distribution, very close to the standard normal. It does have a little bit of difference, especially in the tails. You can see there in the tails, they are relatively different, maybe. For instance, if we take the T distribution and look at how much probability mass do we have to the right side of 2, what's the chance of going beyond 2 for a T distribution of 9? Well, that probability is almost 4% here. What would the similar probability be to go beyond 2 in the standard normal? Well, this is approximately 2.5%. If it was 1.96, it would have been 2.5%. That's the 1.96, right? You learned that last time for the first time. This is, if you're going to remember one number, one quantile in this course, it's 1.96. Later on, I'm going to share the second one with you. 1.96 is the most important one. In daily speech, we call 1.96 2. Quite easy to remember, right? And if we go exact to the probability is only around 2%, 2.3% here. Relatively seen, 3.8% and 2.3% is actually relatively seen pretty different, actually. One is 50% different from the other. So even though at first sight these two distributions, they appear very close to each other, yes, they are. And the higher n becomes, the closer to each other they are. And for n 31 and up, they are almost the same. So it's not a big issue. For high n, for small n, it can be a pretty important issue. This was actually the standard normal and the t, and thinking about what it really means, that a sample mean is something that changes from sample to sample. And the intelligence of the statistical procedure is to realize that variability. And even more so, we can quantify how large that variability is by these distributions and these formulas. So we can work with that. That's pretty neat. Here we go. It's difficult. The middle one is the black, if it's difficult to see the colors. The middle one, the top one is the blue, and the flat one is the black. It's not so easy to see the colors, though. Okay. The original distribution has the sigma, right? That could be anything. Then when I start to look at the distribution for the mean, I take sigma divided by root n, which means this standard deviation for the mean narrows in, right? I divide by n, and n goes up. N is a positive, sometimes large number. So the distribution for the mean is a more narrow distribution than the original distribution. Think about that. Important. Good skips. Now, this was all theory, in a way. I just showed you theorems. And I even introduced a brand new distribution. And let's see if I can. Now to the actual tool. The method that gave us the result of the example in the beginning.